Welcome everyone. Today we are going to discuss on the impact of compiler optimization on high level synthesis results. Okay. So, if we look into these software domains, where if you just see any compiler like C compiler, GCC or any other domains, there are lot of optimization techniques are applied on that, right? Because we have a C code and that is going to map to a assembly level code by a compiler, and maybe that code is not optimized one, right. So, there are a lot of research happen and there is a very rich domain of area in compiler optimizations that are actually applied, and we just see how they are impacting on processor, that execution in the processor of a behavior. So, similarly, when you are thinking about high level synthesis, so we have gone to abstraction level as high as C code, right. So, now we are starting from a C code and we are generating hardware. So, now the question again, how those compiler optimization techniques can have an impact in the hardware that is going to synthesize through high level synthesis, because we have starting from a C code, and so we have the scope to exercise this particular practice just to see how these optimizations can have an impact on the generated hardware through high level synthesis. So, that is kind of the discussion topic today. Specifically, we are going to discuss various optimization techniques, basically on data flow based optimizations like tree height reduction, constant and variable propagation, this common sub expression, operator strength reduction, dead code elimination, code motions, techniques like that, also variable renaming, and also certain compiler optimization technique like model expansion, conditional expansion, loop expansions, and also some recent works on this area. Basically, just to review those techniques primarily with some examples, and then we try to see their impact in the generated hardware through high level synthesis. Okay. So, we will start with this data flow based optimization. Specifically, we will start with this tree height reduction. So, if you remember, when we start discussing on high level synthesis in the pre-processing step, what we do, we just whenever there is a big expression, arithmetic expression, we try to split this expression into small 3 address operation, right. So, that is what we already discussed during this high level synthesis discussions, right. So, and so that is something just to do, because that whole expression is not going to be executed in one cycle. So, try to split that big expression into small expressions and just to execute the small expression in each clock, right. Now, this whenever you are actually breaking these expressions, there are various way to do it, right. So, whenever you do in certain way and there may be various way to do it, and not all of them result in same kind of critical path or the number of time step required to execute that behavior, right. So, that is what is related about this tree height reduction. So, whenever you have a big arithmetic expressions, you just try to split them into 2 operand expression, that is it is 3 address code, such that we can exploit the parallelism available in the hardware at best, right. So, for example, if you take this example of this very simple example a plus b plus c plus d. So, what we can do? We can do this first, right. Then we can do this is say x, and then we can do this plus this c, and then this whole plus d, right. So, that is what is a equal x equal to a plus b, then x equal to x plus c, and then this is x now, then x into x plus d, right. So, this is what I am doing. So, if we just draw that dependency here, so we compute a plus b here. So, this is x now, and then x plus c, this is x now, and then this is final x, right. So, you can see we need to actually so there is a sequential dependency among these operations, and I need 3 cycle, because I can execute this in time step 1, then this is in time step 2, and this is in time step 3. So, I need 3 cycle to execute this behavior, right. Similarly, so and also since in each time step I have only one addition operation is happening, so I need only one adder, right, but I need 3 cycle to execute this, right. On the other hand, if you just execute in this way, that I do this a plus b first and c plus d in parallel, right, because we can do that, and then I just merge these results, right. So, that is what is shown here. So, I just do a plus b here and then c plus d here, say this is y, and then I am doing x plus y, this is x equal to x plus y, which is doing the same thing, right. So, this is doing the same thing, but now I need 2 cycle, right. So, in the first cycle I can do these 2 in parallel, and this is in second cycle. right. So, but I need two adders, right, because now two of addition operation is happening in parallel, but suppose you have these two adder available, then then probably this is a better choice, because now this is taking one cycle less than the other one, right. So, the idea is here is like this tree height reduction is to balancing the expressions as much as possible, so that you can execute operations in parallel which is not dependent, right. And also what kind of impact it is having is like the height is proportional to the lower bound of the overall computation time. So, whatever the tree you are getting syntax tree, the height is basically determines the number of time step is required, which is latency, right. So, or the overall lower bound of the computation time, you need at least those number of time step to execute that behavior. So, if the height is too high, that means your computation time or the number of time cycle time step required or the latency is required to execute your behavior will be too high. So, on the other hand, if you can parallelize, you can do execute this in parallel, now you can actually have a serious impact on the number of time step required, right. So, this is something a technique which primarily did try to reduce the computation time, right, improve the computation time of the generators design, right. And also in some cases this is very simple operation, but in some cases this kind of reduction cannot be done directly. So, we might have to apply this arithmetic properties like say associativity, commutativity or say distributivity, those kind of properties of the arithmetic operators just to utilize this tree height reduction. So, here is some examples. So, for example, you have this, right, a plus b this, right. So, you have in this case you have to execute this first, because this has the higher precedence, then you can do this and then this, right. So, what is happening here? So, b plus c is happening here, then you are doing a plus this, say suppose this is say t, and then this is happening here. So, you are doing t equal to b star c, and then you are doing say t 1 equal to this is say t 1 equal to say a plus t, and then finally x equal to t 1 plus t, right. So, this is what is happening, but again in this case you can see I need three time step, right. I can do this, but if you have just try to directly do this height reduction on this is 1 2 3, do this, it is not possible, because it has the higher precedence, you have to do it. But since you know this adder is a addition is a commutative operation, right. So, basically a plus b is equivalent to b plus a, right. So, this is there. So, I can rewrite this expression like this is basically equal to a plus d plus b star c, right. I can do this. So, if you do this, now I can do these operations parallel, like these two operations. So, what is I am doing here? So, I am doing this b star c here. So, I am doing t equal to b star c. So, this is t 1 and t 2 equal to a plus d. I can do this and this operation now in parallel, right. This is what is happening here, t 2 equal to say a plus d, and then x equal to t 1 plus t 2, right. So, then you can actually do this in 2 time steps. So, this is time step 1, this is time step 2. So, this is something an example just to highlight this tree height reduction is not always possible, cannot be directly applied because of the precedence of the operations, right. The multiplication has the higher precedence over additions and so on. So, you cannot apply them directly, but you can actually manipulate those expression using the this arithmetic operations property like commutativity, distributivity or associativity, just to reduce the tree height reduction, right. So, similarly, here is another example for this distributivity. So, if you have this expression, you have to do this first. So, I have to do this b star c, and then because this is a multiplication, right. So, I have to do this and then this addition will happen. So, I am going to do this b star c, then b star c into d, then I am doing addition. So, this is happening here, and then I am finally I am multiplying this with this multiplication, right. So, I need basically 4 time step. So, I need 4 time step, right, because I need basically 4 1 2 3 4. On the other hand, if I just do the distributive property, because multiplied is a distributive operation. So, I can multiply this, I can get this expression, right. So, then what is happening? So, basically distributive means basically a into b plus c means a b plus a c. So, this is what I am doing here. So, I just multiply a this b star c star d and a into e. Now, I can do this A into E in parallel with this multiplication, right. So, here also I can do this and this operation in parallel. So, I am doing A into B here, and then C into D here, and then multiplying this whole thing to get A into B into C into D. Here I am doing A into E in parallel, then I am doing the addition, right. So, now I can see, you can see I can do the whole thing in 3 time step, right. So, 1, 2, 3. So, again this height is reduced, but directly from that expression I am not able to reduce, but I can only reduce just by applying this distributive operation, right. So, this is just to this is one kind of technique which is called tree height reduction, and as a summary we can actually it is just try to apply to parallelize these operations and just to reduce the computation time, right. So, the number of time step required to execute the behavior, it has a great impact on that, right. And another point is there, just to reduce the height we have to apply this arithmetic operations, arithmetic properties like commutative, distributive or associative operations, just to make it reduce the height of the tree as much as possible. Okay. Okay. So, we will move on to the next kind of compiler optimizations, which is called constant propagation or constant folding. So, as the name suggests, is basically if you have a constant somewhere, right, some variable is basically become a constant. So, you should apply all the occurrence of that variable with that constant value, right. This is as simple as that. So, for example, here suppose after certain kind of optimization your behavior become like this. So, A equal to 0. So, A is 0. So, A is a constant now. So, we should apply wherever the A occurs, you should apply this 0 directly, right. So, for example, here if I just apply this A equal to 0, B will become 1, right. So, this is something is called constant propagation. So, I am propagating A to this location. So, your B will also become a constant, and the important feature is that whenever you propagate a constant, some other variable also become a constant, might become a constant, right. For example, here although B is a expression, B has a expression A plus 1, but because I am propagating A is a constant, this right hand expression is evaluated to become a constant, right. Now, I should propagate B also, right. So, I propagate B to this expression. So, B equal to 1. So, this will become 2 into 1 is usually 2. So, all these things become constant, right. So, this is what is called constant propagation or constant folding. So, so this is something we should always do this, because what is the advantage of having it? So, basically if you have this A plus 1 operation or 2 star B, these are the operations, this has to be executed, right, in the hardware. But if you propagate some constant and some expression become again constant, you do not have to execute that operation, right. So, it has an impact on the resource as well as in the computation time, right, because if you try to execute this operation. So, for example, this, so you have to execute this is A is coming. So, this is A plus 1. So, in this first time step this is become B, and then you have to do this multiplication, right. So, you need at least this is 2. So, this is become C, because see this operation depends on B. So, you need at least 2 time step to execute this, right. So, on the other hand, if you just propagate this constant, this all are kind of variable assignment. I mean, this is, it can be done just in one cycle, right. So, this is the advantage of having constant propagation, and it has impact both on in the resource as well as in constant computation time, because I can improve the constant time by just not executing those operations, because those are becoming constant, as well as I do not have to store these variables now, right. I do not have any some temporary variables or some intermediate result I do not have to store, or say I do not need a adder or a multiplier in the hardware. So, it is basically having impact on the resource as well. So, it might reduce the number of registers, it might reduce the number of adder, multiplier, that is in summary the hardware resources, multiplexers as well, and also computation time, because I do not have to execute those operations in the hardware now, right. So, this constant propagation and constant folding is kind of, or a constant folding is and very simple operation, but it has a some significant impact on the generated hardware. Okay. So, we will move on to the next kind of optimization, which is called variable propagation or copy propagation. Just like constant propagation, here if some variable is assignment operation, right, say A equal to B, this kind of operation, then we can utilize either A or B, or say I can use only B, right. I do not need A, right, because that is they are the same value, right. If A equal to B, then this, or so for example, in this example a equal to x. So, x and a are basically the same value. So, in this case I can use only x, I do not need a, right. So, that is what is called value propagation, variable propagation or copy propagation, because whenever some copy operation is there, assignment operation is there, you just take the right hand variable and you just replace all the occurrence of the left hand variable in the next operations. So, what is here is some example. So, a equal to x. So, what I can do, I can just eliminate b, I can use x wherever a occurs, right. So, I replace this a by x, this a by x, and I just so now this operation is basically become a dead code, right, because I do not need this. So, I can delete this. So, this is called dead code elimination. So, finally, this will become this, right. So, now we can do some other operations, is something operator strength reduction that I will discuss later, but essentially this is what is called value propagation or copy propagation, right. So, what is the impact? Definitely it has impact on the register, because I am now removing some of the variables a. So, I do not need a register to store a. So, this definitely have some impact on register number of registers. Okay. And also the important factor is like, once you have done this, it might enable other optimizations, right. For example, here it enable dead code elimination, and in some scenario it might also enable operator strength reduction or constant propagation or other kind of optimization. So, in general, and we do not have to maintain two different kind of variable, two registers, their interconnections, right. So, all those complexities will come. So, it has an impact directly on the number of resource we need, right. So, this is something an important operation, simple but useful operation, right. So, also one point to be noted here is that we cannot just replace blindly all occurrence of a, right, because if a is redefined here, right. So, then you cannot just use it, or in other way, if the different reassignment of x. For example, suppose a equal to say x and then say b equal to a plus 1, then x equal to say x plus 2, then say again c equal to a plus 5. I cannot, I can replace this, right. I can replace this because now this x is same, because the same value is happening here. So, I can just do a equal to x, then b equal to x plus 1. This is a copy propagation, and since now this x become x plus 2, I cannot use here x, right. This is not allowed, right. Then because this x and this a is not same, because whatever the value of x here is modified here. So, I cannot use it here, right. So, I cannot just remove this operation, this is not a dead code, but I can again I can always do this copy propagation, but I should avoid doing this replacing this a by x. So, it should remain as a, right. So, this should remain as a, and I cannot delete this as a dead code, right. So, this is what is this constant copy propagation, but you have to keep in mind that I cannot just replace all the occurrences of a, because in some time that x might be reassigned or redefined, then that has a different value now. So, we cannot just use x for the subsequent operations. So, those things can be just checked by data flow analysis, right. So, those who are comfortable with this compiler, they know all those terminologies and they know how to doing this kind of check, right, which can be done, which cannot be done, right. Okay. So, I will move on to the next set of optimization called common sub expression elimination. So, as the name suggests, whenever there is some sub expression which is same, right, common, I have two operations where the right hand expression is same, I can use only, I can execute that sub expression only once, right. So, that is what is called common sub expression elimination, and I can use that particular value for the subsequent requirement, right. So, that is what is called common sub expression elimination. For example, here you can see I have x plus y, I have y plus x, but this is a commutative operation, this is basically x plus y. So, these are the common sub expression. So, I can just only execute once, and whenever I have this occurrence, I can replace this by a, right. This is what is happening here. So, this is what is called common sub expression elimination. So, it is what is the impact of it have in the hardware? Obviously, you can see that I do not have to execute this is 2 times. So, obviously, it is saving resource as well as computation time, right, because here if you just try to do it, it will take 3 cycle, right, because or maybe in 2 cycle. For example, here you are doing this say x plus y, right. So, you are doing x plus y, you get a here, then you are doing here plus 1, this you are getting b, and then say you are doing c plus. So, you can do although this is you can do here again this is your c, right. So, this is again the same x y, right, x y x y x y y, but you need 2 cycle. On the other hand, if you just do it, I am not going to do this this operation. So, again, so I know I do not need this resource. Instead, what I am going to do, I am going to do this once x and y, and I am going to assign this to both a and c, right, and then in the next cycle I can do this plus 1. So, although I am not reducing the number of time step here, but I am actually reusing these results to define the both the variable, right. So, effectively I am actually reducing the number of resource, at least for this example, but in some scenario we might see that if the number of common sub expressions is many. So, that expression may be in 5 places, I do not have to execute in 5 times. So, it might also save your time. So, it can also impact in the number of computation time as well, right. So, that is something is there. So, let us take another example of common sub expression elimination here. So, you can see here one common sub expression is b plus c, right. B plus c is a common sub expression. Similarly, I have another common sub expression is b star c, right. There are 2 common sub expression, b plus c as well as b star c. So, can we replace this b plus c? Yes, because in this case b and c is not updated in between, right. So, if b and c is updated in between, then this b plus c and this b plus c is different, right. So, but here in this portion of the code b plus b or c is not updated, right. So, I can store this b plus c into some temporary variable e dash, and I can use that e dash for both this expression and this expression, right. So, this e and b both can be defined using this, right. So, this is what I have done, right. So, now you can see here I can do these things in parallel, because since I have dependency on this some other operations, in other cases I cannot execute all of them in one time step, but now I can do them in one time step, which is saving your own time step, right. But for the case of b star c, here b star c and this b star c is not same. Why? Because because in this portion of the code your b and c should not change, but here b is updating, right. Since b is updating, so this b and this b is not same, right. So, I cannot replace this expression by this value of e f q, right. So, this b star c cannot be eliminated. So, this is also again you have to keep in mind that we just cannot blindly just replace all those expression. We have to specifically do some data flow analysis just to find out whether those b and c is same in all the places or not, right. Then only you can do that. So, you can see in this example, but doing simplification here I need one this is one time step effectively, this is another time step, this is another time step, 4 time step, right, 1 2 3 4, here I need 1 2 3 time step, right. So, I am actually saving one time also, right, one time step also. So, that is what I just saw ki your common sub expression can have impact on both resource as well as in time. Okay. But you have to always keep in mind that I cannot just replace all the sub expression without checking the data flow or data dependency among the operations. The basic bottom line is that between 2 operations, all the variable that occurs in the right that sub expression should not be modified, right. So, they should not be redefined again between the two sub expressions, right. So, in that case we cannot just replace, and this example just clarify that particular point. Okay. So, I will now move on to the next set of operation optimization called variable renaming. So, again this is a operation where you just rename some of the variable, but what is the impact of that? It might just reduce the dependency. Some sequential dependency is there among some operations, you just rename some variable, and that so that this dependency goes and you can execute these two in parallel, right. So, that is what is called variable renaming. You can see here. So, what is happening here? So, m is equal to a plus b, right, and then m is using here, and again m is defined here, right, and m is going to use here. So, you can see here I cannot do all this operation parallel, because this operation depends on this. Unless this operation execute, I cannot execute this. Unless this execute, I cannot execute this. So, I need 4 time step, right. You can see here. So, this is time step 1, this is time step 2, this is time step 3, this is time step 4, right. I need 4 time step to execute this behavior, because there is a dependency. But on the other hand, if I just redefine this variable, because this m does not depend on this, instead of m I can just make it m1, right. How does it matter? Because this is not the final output, right. So, if I assume that final output of this or I can just assign this here. So, I can just redefine this variable, so that I can just break this dependency, right, this write after read, right. So, this is write after read dependency, which I can break here. So, that I can just execute this m equal to a plus b and this m1 equal to d minus b in parallel, because these two do not depend to each other. And then in the next cycle I can do this assignment and this assignment, right. So, n equal to m minus c and o equal to m plus f. I can do this execute, and since my final value of m is this value, I can just do m equal to m1, right, because this is that my final value. But you can see, by doing this variable renaming, I just reduce this write after read dependency. As a result, I can execute these operations in parallel, and I can execute the whole behavior in 2 cycles. So, this is variable renaming definitely helps in improving the number of time step required to execute an behavior. So, hence the computation time. But on the other hand, I am actually defining some variable. So, I may need some extra register to store that variable. So, that may increase the number of registers, right. So, this might have some little bit side effect, but it has, if you have a lot of this write after read dependencies, then definitely this is going to break that particular dependency, and you can execute your behavior in less number of time steps, right. This is what is called variable renaming. Next set of optimization is dead code elimination. As the name suggests, if some code is dead means what? That the value that is defined there is never used, right. So, whatever the definition you are actually defined in some expression is basically dead, right. It does not have any use in your behavior. So, in that case you can actually remove that, simply remove that particular dead code, right, because it does not have any impact in the generated output, right. So, for example, here you can see a equal to p plus q, and then you have b equal to x plus 1 and c equal to 2 into x. This does not have any impact here, right. So, I can simply delete this dead code, and my final operation will become b into b equal to x plus 1 plus and c equal to 2 into x. So, what kind of impact it might have in dead code elimination? Obviously, I do not have to execute this p plus q. So, it will reduce the number of arithmetic units, because I do not need to execute that, and also I do not have to execute this. So, I may save some computation time, because I do not have to need another resource to execute that. So, that might increase the number of time step required to execute. Similarly, whatever the express variable that are in the right hand side, they may also be redundant. They do not may have some use in other places. So, if I just delete this or eliminate this dead code, I do not have to store p and q as well, right. So, this may also reduce the number of registers. So, dead code elimination in general impact in all places resource, in the sense number of arithmetic units, number of registers, as well as in the computation time, right. So, this is what is dead code elimination. So, next optimization is called operator strength reduction. So, what does it mean? So, there may be some operation which is complex, right. So, like multiplier. So, multiply by constant, right. So, this kind of operations can be replaced by a simple shift operation. So, I am actually doing the same operation, but I am doing using a less complex operation, right. So, I am just reducing the strength of an operator, or say I have x square. So, I need a multiplier x into x, but instead of doing x into x, I can just do x plus x, 2 into this case I cannot do, but what I can do, this constant multiplication is a place where I can do it. So, 3 into n. So, there what we can do, so here is an example. So, I have say n into n square. So, I can do n into n. So, I can then what I can do this, I have 3 into n, right. So, I can do 2 into n then plus n, which is basically 3n, right. So, whenever you have 2n, I can just do the left shift, right. So, whenever you are shifting some by value of say 5, you have say 5, right, 101, 1001 is what is 9, right? This is 9. If you just do it left shift 9 left shift by 1, what will happen? So, we are shifting the whole thing by 1 bit. So, 10010. So, what is that? So, this is basically 18. So, basically when you are shifting some variable, it is just doubling the value. So, I just make a shift. So, I will get 2n, then I can just do the addition, right. So, instead of doing using a multiplier, I am using a less costly operation shift. Shift you just you do not need basically any operator, right. You have to just do the bit manipulation. You have to just shift the whole thing by 1 bit. You do not need any adder, multiplier or any kind of resource just to do this. You just shift and you reassign the value to these bits, right. You have to just do A1 equal to A0, A2 equal to A1, A3 equal to A2 and so on, right. So, you have to just do that, it will automatically do the shifting, right. So, this is something is done. So, I just break this 3 in 2 into plus, and then I do this by shifting, and then I just do make addition. So, multiplier can be replaced by a shifting and addition operation, right. So, essentially you can see it has a impact on the resource optimization, right, in the resource, right, because a multiplier when you are going to implement it, it is a complex big circuit. On the other hand, if the shift is nothing, just a bit manipulation, bit assignment, and I need a simple adder, right. So, the adder is much simpler circuit than and a multiplier. So, this operator strength reduction is useful just to reduce your resource of your design, right. So, some other example is this is one kind of thing where you can actually replace this multiplier by shift and add kind of operations. So, on the other hand, if you have some operations which is basically inside the loop and which depends on that inductive variable I. So, I is the inductive variable which is basically iterator, and some variable which is basically invariant to the loop. C is not changing in the loop, right. So, this is a loop invariant. So, if some expressions are there which is depend on the inductive variable as well as some loop invariant, I can replace those kind of expression by a simpler operation, right. So, what is happening here, you can see here. So, C is initially 7, what I am doing here, y 1 equal to basically y 1 equal to what, sorry, y 0 equal to I equal to 0. So, this is 0. So, y 1 what, this is basically C, right. Now, this is I equal to 1. So, 1 into C is C, then y 2 is what, 2 into C, right. Y 3 is what, 3 into C, and so on. So, this is what is happening. So, now you can see here this these successive expressions. Instead of doing this multiplication, I can compute this 2 C from this only, right. So, I can do this whatever the value here y 1, this I can do y 2 equal to y 1 plus C, right. Similarly, y 3 what I can do, this is 3 C, this is 2 C plus C. So, I can do y 2 plus C, right. So, I can just do this way. So, y 4 equal to y 3 plus C. So, instead of doing this multiplication, I can just do this, right. I can do the same thing by an addition operation. So, this is what I am doing here. So, I have initially k equal to 0 because this is C 0, and then this is y equal to k, and I am just calculating this directly. I can do this, or I can just calculate this because my k is that the previous value, and then I just add C, and then I am assigning this to here, right. So, it is effectively doing this, right. This is effectively doing this. So, what I am doing here is instead I replace a costly operation or a complex operation multiplier by a addition operator, and this is applicable to this inside the loop, right. This specifically this kind of strength reduction looks for expression involving a loop invariant and a inductive variable, right, and just some of these cases this can be replaced by a weaker addition operation, right. So, that is what is happening in this particular cases. We might have some other cases of operator strength reduction, like, so if you have say division operation, right. So, division is basically right shift. So, for example, say suppose your x equal to say 16, right. So, you are doing x by 8, 16 by 8 basically 2, right. So, this 16 means what? This is 16, right, this is 16 and 2 means what, right. So, now if you just do this 3 right shift to this, so this 3 will go. So, this 1 0 and this 3 extra 3 will, which is basically 2, right. So, this division by some number which is basically power of 2 can be replaced by just simply right shift operation, right. Similarly, what I just seen that multiplication can be replaced by a left shift operation. So, this and this factor can be this multiplication, I mean power of 2, right. 64 is basically 2 to the power 6. So, I can just make a left shift of 6, right. So, but as I seen in this example, if it is not multiplication of this, then I can find the nearest a power of 2 and plus some addition operation, right. For example, suppose you have in this case you have 66, you can do 264 into x plus x into x, right, or maybe 2 into x. Then I can do this 6 times and then I can shift by 1 bit and then I can just add it, right. So, this I can do also. This is also shown here, or if you have say 15, then I can do, this is what I am saying, I can do the 16, the nearest power which is 16 and then I can do this 1 minus, because this becomes 16 x and then I just make a minus x, so that it becomes 50. So, the idea is that whenever you have this division or multiplication operation, I can always replace them by and shift and addition operation, right. And idea is that if it is exactly multiplier of 2, sorry, a power of 2, then I can directly do the shifting. If it is not, then I can find the nearest power of 2 and then I can do either addition or subtraction based on the value we obtained, right, after shifting. And also we can do operator strain reduction by eliminating this inductive variable and this loop invariant variable, right, in case of loop. So, these are this operator strain reduction, and this usually have an effect in generating hardware in terms we are replacing a complex big operation by a simpler weaker operation, right. But we are effectively doing the same functionality or achieving the same functionality in the design, right. This is what is called operator strength reduction. So, I will now move on to the next set of optimization, which is called code motion, and it has very good impact on the generated hardware. What is the code motion? As the name suggests, is basically moving the code, right, moving the code in your behavior, and your movement can be anywhere, right. So, it can be before loop to after loop, from the loop to outside, or from the outside to inside the loop, or maybe there may be some if else block and you are moving some operation before loop before the if else to inside the if else, or from if else to outside, right. Both is possible. So, all kind of possibilities there, and you based on that we actually can have a different kind of code motion, which is called duplicating down. Basically, suppose I just consider a if else here, you can have also loop, right. So, this is your if else block, right, this is your if else block. So, in this, so you are moving some operation from before the loop, before the if else block to inside the if else block, this is 1, right. So, this is 1. So, this is duplicating down. So, duplicating up is I mean whatever is. So, this is your effectively this is your if else block, sorry, this is your if else block. So, this is your if else block, right, this is if else block, and if some code after that you can move inside the if else, right. This is called duplicating up. Boosting up is what? Boosting up is basically from the loop to outside, right, or boosting down is from the if else to after the loop. This is called boosting down, or it can have across, right, something here you can move it after the if else, or this may be a loop, you can do that, right. So, you can do across loop as well. So, there can be various kind of code motion and it might have some good impact, right. So, there are some example. So, duplicating down. So, here you can see there is operation here which is before the if else, right. What I am doing here, I am just moving this duplicating in both the path, right. What is the impact of that? You can see I just move this operation to this branch and this branch also. So, this is here and this is here, and what is the impact? Because this D is not using in this branch, so I can do this operation and this operation in parallel, right. On the other hand, since this D is using here, so I need 2 cycle here. So, the advantage is here is that if the behavior is executing through this branch, then what is happening? So, I need 1 cycle 2 cycle and 3 cycle, right. So, I need 3 cycle to execute the behavior, but here you can see if this is happening through this branch, I need 1 cycle and another cycle. So, 1 cycle. So, I am saving 1 cycle in conditional execution, but whenever the execution happening through this, I need still 3 cycle, right, because I have to do this in this. But at least if, because in your behavior this if else might execute multiple times. So, in some time you are actually saving one clock, right. That is what is the advantage of having duplicating down, right. So, because in some scenario that particular operation may not depend, is not used in some particular branch of an if else, and there we can do that operation in parallel. So, that will give you a saving here. So, as I shown here, I have one time step saving in the if branch, right. Boosting up, I am giving some example of them. So, boosting up is something, suppose you have an operation here d equal to x plus y, I want to move it to before the if else. So, this is your if else block, right. And if you just try to do it, because this variable is used only here, right. So, if I just put d equal to x plus y here, that d might be used here, right. So, there may be some operation here which is basically say x equal to d. So, then this d plus 1 say. So, this d is not this, right, there may be some other d defined here, d equal to say 1. So, I am going to use this d here, but if you move directly this operation here, then this value of x will come here, which is wrong, right. So, that is why whenever we do the boosting operation, you need to store this as a temporary variable, right. What I am doing here, this d equal to x plus y boosting off, I do it before the if else, but I am storing this into d dash, and I am going to use this d dash here, right, and this d dash have no impact here. Again you can see here that this particular operation I am boosting off, and it might impact, though this is not visible in this example, that maybe I am actually saving some time step, because this particular, actually I am doing this because I need 2 cycle here. In this case you can see here in the if this branch, right, in this branch I need 2 cycle, in one cycle I have to do this, in the next cycle I have to do this, right. But in after scheduling, after boosting up, I can do this operation in one cycle. So, if there is an execution through this path, after boosting up I am saving one time step, right. So, this boosting up also again you can actually, it can improve your computation time by just putting some operation before the if else block from one branch. But you have to keep in mind that when you are moving that, you cannot just use the same d, because that may have a, that d might have some different use in the other branch, which might be affected by this d. So, I have to store in some temporary variable, right. This is what is the idea of boosting up. Just to give example of duplicating off, here there is an operation after the if else. So, this is your if else, and I am just duplicating off both of them, right. So, what I am doing here, I am just moving this to this branch and this branch. Again you can see this operation is not depend on this values, this a is computing here. So, I can do this them in parallel. So, earlier how many time step was required? 1 for any branch, I need one branch to do the if or else, and this 3. There are 3 time step, now I need only 2, right. One time step for this, one time step for either doing this or this, right. So, I have need only 2 time step instead of 3. Again this duplicating down can improve your computation time, right, duplicating out, sorry. So, in this way we can actually give other kind of example, but this is just to highlight that this kind of duplicating down or say boosting up or say duplicating up, this kind of examples have an impact in the directly impact on the computation time, but in conditional branches, right. So, not directly, if you just saw it blindly you may not see the effect, but if your behavior execute through a particular branch, then your computation time might improve, right. So, as I discussed that reduce the schedule of operation, the total computation time definitely, right. There is another big impact of code motion is something, it reduces the lifetime of a variable, right. So, what I am doing actually I am moving an operation from one place to another place, right. The idea is that if some operation defined here, right, very early, and it is going to use very late. So, that particular definition has to store in some register for a long period of time, because unless this is going to use here, I cannot remove that particular value from the register, right, because then that value is required here. So, defined and use. So, I have to store that variable for that long, but if I move the definition and this use close by, then I do not have to store it for long time. This is just going to give an example. Suppose I define A here, and there is a long sequence of code. So, there are 100 line of code where I do not use A at all, when I am not updating A at all, and then I am using it here, right. So, that means I have to store this A for, say, this is a 100 cycle, I have to for 100 cycle. But in code motion, suppose I just move this operation and to near to this, right. So, this operations where this there is no use of A, or there is no definition of A here, right. So, there A is this part of operation is independent of A. So, what I can do, I just move this operation near to this definition. So, now so maybe I have to just in one cycle I can just define and can use it. So, instead of storing this for 100 cycle, I can just store that variable A for one cycle, right. So, that means this code motion directly impacting this, reducing the lifetime of a variable, and effectively this is reduce the number of register. As you have seen that we can store 2 register if their lifetime is non overlapping, right. That we have already discussed in during high level synthesis discussion. So, so we can actually reduce the number of register that is going to be required to store all the variable, right. That is another impact of code motion. The third impact of code motion is something is the number of operations also, right. The repeated operation also can reduced. For example, here suppose I have a loop invariant operation t equal to a plus b, because a and b is not updating here, right. So, this is a constant operation. So, instead of doing this for n times, I can do it only once, right, and I can use this t inside, right. So, then I do not have to do it for so this n is 100, then I am not doing this 100 times, I am doing only 1 times. So, this is also saving computation time, right, because I do not have to do this operation for multiple number of times, I am just doing only once. So, this is also have a good saving, because if you just have a iterative iteration implementation of this loop, I am effectively saving 100 number of cycles, right, because I do not have to do it 100 times, right. If this operation particularly inside the loop, then it is going to execute n number of times or 100 number of times, but if it is outside the loop, it is going to execute only once, right. So, so code motion is very useful technique, and there are a lot of works actually happening recent times just to show that what are kind of impact, right, in of code motion in generated hardware, and it has impact on number of computation time, number of operation to be executed, and also as well as the lifetime of a variable, and hence the number of register required to store this variable. Those who are interested, you can go into this kind of technique like reverse speculation, you can search internet, lazy execution, early condition execution, like speculation, loop shifting, right, or say branch balancing or conditional speculation. So, there are a lot of specific type of this code motion. I am not going to detail of each of them, because this is can be a whole new topic, the code motions, different kind of code motions, and there are a lot of work actually going on. They are actually showing the impact of say conditional speculation in generated hardware, or say branch balancing in generated hardware through high level synthesis, or say speculation, loop shifting, early condition execution, say reverse speculation. So, those are specific type of code motions, and there are a lot of studies happening on that. So, those interested, you can search for those kind of work, right. So, now I am going to talk about this control flow based optimizations, and here I am going to talk about specifically 3 kind of technique: model expansion, conditional expansion, and loop expansion. So, what is that model expansion? Is basically just replacing that function body by the body, right. So, if you remember when I am talking about this code, coding style. So, what I have discussed that whenever there is a function, it will create a module in the hardware, right, and if that function is going to call multiple places, I am going to reuse that particular module if they are non overlapping, right, if their schedule is non overlapping. So, that is how this function is going to synthesized, but in certain scenario there is a very small function is only called once, right, they are not effectively calling multiple times. So, then instead of making a function or module for a function, I can replace that function call directly by that function body. Now, what will be the advantage? Because whenever you have a module, you have to keep track, there will be some control, there will be some extra control signal. So, there will be other complexities come into that, just maintaining a module, right, and it just have only one use. So, there is no point maintaining doing all those extra things just to maintain that module for one call, right. What you can do is just replace that call by the function body, The advantage of that is that now this all the optimization that we talked about so far can be applied on the whole code, right. Whenever there is a module, whatever the optimization, that will be local to that module, right. But and whatever the optimization happening in the main function, that is local to that. So, whatever the optimization, that does not go into this module to optimize something, because that is a different module, right, that might have some other use somewhere. So, I cannot do this context specific optimization, but if I replace that function call by that function body in that place, now I have more scope to apply optimization in the whole set of code, right. So, that is a big advantage, that will actually give you some benefits on in terms of resource number optimizations. But the bad side of this particular, or say negative side of this particular optimization is that if that particular function is multiple calls, then I should not do it, right. Then basically if I just do it, it just increases the code size, right. Instead of one module, if there are say 10 calls, I have 10 body to be replaced, and if the body is big, then it increase the code size, and hence the number of operation to be executed, right, because if it is become modular, it is only one hardware required for that, but I need 10 copy of the hardware if I just replace that function body, right. So, that is something the negative side of this, and you should do this kind of model expansion only if we have only one or two call of a function, right, in this. So, here is an example. Suppose I have, this is my main code and I have a function call here, and this is doing nothing, just doing say p plus q, it is q plus p. So, now I can replace this function call by this function body, right. If I just do it, since I call through a b, I can replace this q plus b by b plus a, right. So, this if I do the model expansion, my code will become this. Now, by applying these common sub expressions, I can replace this two are common sub expression, I can replace them, right. So, I can do this x equal to a plus b, and I can just do z equal to x. So, that is actually improving. So, in this case I cannot apply common sub expression elimination, because these two are two different body and these two different expression, I cannot do that. But once I apply this model expansion, now it increase the scope to apply other optimization like common sub expression elimination. In this case, I can replace this common sub expression by a single, right. That is what I have done, and I am not done yet. I can have some other optimization now. So, now this is become a copy operation, I can do the copy propagation, right. So, I can just do this do here. So, I can just do it x here. So, once I do this x equal to x, then I can replace this, right. Then this out will become only y, right. Then once I do this x equal to a plus become dead code, right, because that has no use. So, effectively this become out equal to a star b. Again I can replace this y, because I do not need to store that, because this is happening here. So, effectively this whole code is doing a out equal to a star b. So, this is just to highlight an example, just to highlight that if you do the model expansion, that will increase the scope of application of the other optimizations, and that might reduce the code by a significant amount. So, that is the advantage of model expansion, but you have to always keep in mind that if that particular function foo says multiple places, then it is not a good idea to replace all the call by a body, because it will you have to execute this operation those many times, right. So, there should be some trade off between this model expansion, whether you should do or not in certain scenarios, or maybe if that particular function has say 10 calls, we might just replace 1 or 2 calls, because that might, if we see there is a very high chance of having other optimization possibility of application of the other optimization in certain places, we can actually replace those calls, but I can keep other calls there. So, that I can use that function body for other calls, right. I can reuse that particular function body or the hardware corresponding to the function body for those other calls, right. So, there might be some trade off, and that has to be analyzed based on your application or the example that you have, right. So, I will move on to the next topic is called conditional expansion. Conditional expansion is basically when you have a say conditional expression like if say C say I am doing something and else I am doing something, right. So, I can always do say I am doing say here S. So, I can always do C into S plus C bar into the C bar into so this is say T, right, C bar into T. I can always do that. So, now instead of doing this in sequential, I can do it in parallel. So, here is an example. So, So, suppose I am doing, if A equal to true, then I am doing this, else I am doing this. So, I can rewrite this whole thing by this, right. Instead of doing this in conditional, I can do everything in parallel, right. This is A into B plus D and then A bar into B D, right. This is what I can do. So, this is what is called conditional expansion. I am replacing the conditional body, because whenever you have conditional body, you have some marks, some decision maker whether it will go do this or that. So, all this conditional signal will be eliminated, I can do it directly, right. This is what is the advantage of the conditional expansion. But the disadvantage is that earlier in hardware I have to do either this or this, I do not have to do both, right. Suppose this is also B minus D, probably I can use the same ALU which can do plus or minus to do both the operation, right, because they are mutual exclusive operation, either this will be executed or this will be executed. So, in hardware I can share a resource for this, right. So, for this, if I suppose this is B minus D, I can just do B and D, and I have only one control signal that will decide whether plus or minus, right. Then it will just do this, if either B plus D or B minus D based on A, right. This is basically A equal, this is A or not, right. So, if it is A, this will be done like this, right. So, so I can share this resource for both the operation, but if you just do it here, I have to do both the operation, right. So, if instead of B D, I can do B minus D. So, I have to do both B plus D as well as B minus D, just to in this case. So, this is the negative part of it, it will increase the resource, but I can do, instead of these things, I can do in all these things in parallel. And another advantage of doing this conditional expansion, that it's, if these variables are Boolean variables, right. So, it actually increase the scope of application of logic optimization, right. For example, suppose this is your Boolean expression, I can do certain kind of optimization, right, some manipulation, Boolean manipulation, and finally, I can reduce the big expression by a smaller expression, right. This is what I can do. So, that is another advantage of conditional expansion in case of Boolean variables. So, I can apply some Boolean logic optimizations just to get a simpler version of expression, right. Instead of doing all this bigger expression, I can have a simple operation to be done, right. That is another advantage of conditional expansion. So, I will move on to the next topic, which is called loop expansion. So, this loop expansion is nothing but loop unrolling, right. If you have a loop body, you just unroll it and replace by the whole loop body by a series of operation, right. So, for example, here suppose you have this loop where this I is going from 1 to 3, I am doing this, I can replace this loop by this, right. I can just do x equal to x plus a1, then x equal to x plus a2 and then x equal to x plus 3. So, I just replace this loop by this, right, what is called loop unrolling. And what is the advantage of having this? The advantage is that once you have done this, probably you can actually apply the other kind of optimization. For example, here I can apply tree height reduction, because this is nothing but doing these things in series, right. So, you are doing x plus this is your x, you are doing this is a1, then you are doing this is your x, you are doing a2 and then you are doing this is your x and this is a3, right, and then you are getting x. So, instead of doing this, you can do in parallel, right. So, I can do this x equal to, this is basically you can do a1 and a2 and this is your x, and then you can do a3, this is your another addition, this is your a3 equal x, right. So, instead of this 3 time step, I need basically now 2 time step, right. I can do it in 2 time step. So, basically idea is that when you have to do this unrolling, it actually widens the application of other optimization, so that you can optimize your code. And also the advantage, and also another advantage is that you have to maintain all this condition, this control signal will be more here, right, because you have to check whether this I less than 3 or not, those things you have to maintain, but here you do not have to maintain. So, the complexity of the controller also will get reduced if you just do loop expansion. But you understand that if this loop is very, the number of iteration of the loop is very high. So, if you just unroll blindly, it will increase the code size by a large, right, and that is not something is good, right, because if you say this instead of 3 you have 3000. So, now you have 3000 operation, it has to execute it, right. That is may not be a good idea to do execute, right. Instead of doing it, it is better to do it through loop. So, you should have some trade off. So, sometimes we just look for partial unroll instead of whole things unroll. So, there are say as I mentioned, I unroll it, say your loop is say 3,000 times, running 3,000 times, I can unroll by 3 only. Then I am doing 3 operation in one loop, and I am going to execute the whole loop 1,000 times. So, I can also go for partial unrolling if your my loop iteration is too high, right. So, you should always think about a trade off between the code size versus this controller size, or the kind of benefits that you are going to have if you have loop body, what is called loop unrolling. So, in fact, this loop transformation is very important in the context of hardware synthesis, because loop has a huge impact on generating hardware, right. So, a lot of works has been done on this. People are trying to check what kind of loop transformation is going to improve your locality of references, so that during successive operation you do not have to read multiple data from your from array, so that whatever operations happening through some variable values, that are going to be done together, right. As I mentioned earlier also, that whenever you have a loop, or say a loop and you have a array is going to be mapped into memory, and in memory we do not have multiple ports, right, we have only 1 or 2 ports. So, if you have say multiple access, 4 or 5 access at a time, I cannot execute all of them in one clock. So, I need multiple clock. On the other hand, if I found key A5 is going to use say 5 scenarios, so I can do those 5 operations together, right. So, then I can read A6, and whatever the value operation is going to depend on A6, I am going to do that. So, if we just do some certain kind of loop transformation, so that all this operation which has a locality of references, a greater locality of operations has happened in successive iterations, that will improve your number of memory read, and hence the number of time required to execute that, right. So, that is something I mean lot of work has been done, and loop tiling is one kind of operation, or loop skewing another kind of operation which actually improve this locality of references. Also, people try to do it merge 2 loop fusion, or loop merging, try to merge two loops, so that you can do some kind of parallelization, or number of time step is required to execute, that can be eliminated, or other kind of optimization just to improve the pipelining opportunity, like loop reversal and certain like this. Actually, in fact, there are a lot of loop transformation techniques are there, and there are various work actually done on this, just analyzing whether what kind of effect of certain loop transformation have in the generated hardware, and that is in fact is another discussion topic, that may be another lecture just to discuss on that. So, instead of going into detail of that, because this is just to give you a highlight that loop is an important factor, and there are a lot of optimizations, and that has a significant impact in the hardware, right. So, that is just I am going to highlight it, and those are interested going to much detail of this research area. Just for your references, I just copy some 4 recent work that actually working on this loop transformations and then impact on high level synthesis. This work was for example, is working on the optimization of memory hierarchy allocation for loop transformation for high level synthesis. Similarly, this is working on loop splitting for efficient pipelining of high level synthesis. This work is working on say high level synthesis optimization opportunity through polyhedral transformation. Polyhedral is another way of applying loop transformations or representing loop, and this paper works on that, how to improve the optimization opportunity through loop transformations. Another work is something impact of loop unrolling in controller delay high level controller delay in high level synthesis. There are many more, so this is just as a starting point for you. And since we have already discussed about this loop expansion or loop unrolling, I am going to discuss this work briefly, just to give you the what kind of impact of loop unrolling on the controller delay. Okay. So, if you take an example of this, right. So, you have an example where I am doing this for 32 times, I am doing this operation, right. So, I just as I mentioned, I am going to partially unroll, I just unroll by 2. So, what I am doing here, I am doing 2 operations in the loop, this 2 successive iteration. I am increasing the loop iteration by 2, earlier I am increasing by 1, and I am doing it 16 times, right. Earlier it was I am doing it 32 times, I am now doing 16 times. And if you just draw the data flow graph, I am doing this loading operation. Loading means basically memory read, right. So, I am just read Zi and Xi, and then I do this multiplication. I am doing the multiplication. I am assuming that I have multiplication is 2 cycle operation, and this load, addition, comparator, all are basically single cycle operation. And I have one multiplier, one adder, one comparator and two load are available, right. And then I just do this x into z is after 2 cycle, I just do q equal to q plus this, right. This is what I am doing here. And in this place I am just doing I equal to, I just do I plus 1 and then check whether this is less than 32 or not, right. So, what I do just to execute this I need 4 cycle just to satisfy the data dependency. Since this is going for 32 iteration, roughly I need 128 clock cycle. I need some 1 or 2 clock step to initialize and all those, I just ignore that, but roughly I need 32 into 4, 128 clock cycles. On the other hand, if you have this partially unroll, I have this load here xi zi, then I am doing this xi into zi, and then I am doing q equal to q plus, right, q plus this xi zi that I have done, and here I am doing this I equal to I plus, because this is I plus is used. So, I do I plus 1, then I am reading this x I plus 1 here and z I plus 1 here, and then I am doing this multiplication for 2 cycle, and then finally add this result with this, right. This is my final q, and this part is similar to this. I am doing I plus 2, because now it is going to I plus 2, this is I plus 2, and then it is just checking whether it is less than 31 or not, right. So, you can see just to satisfy the data dependency here I need 6 clock steps, right, and this is I just mentioned is going to execute 16 cycle. So, 6 into 16 I need 96 clock cycle. So, you can see directly I have savings of 25% of clock cycle if I just do it partial unroll by 2. So, it is good, right. I have a very good impact of unrolling in the number of clock cycle need to execute this behavior. So, it is good, but let us now try to show in the another angle that what is the kind of impact of this unrolling, because this unrolling factor can be different, right. So, this is I just do it for unroll by 2, I can do it unroll by 4, 6, 7, 8, 9, 10, 11, 12 anything, right. I can do partially unroll by anything. So, we will try to this work specifically try to find out what kind of impact of this unrolling in the latency, the number of clock cycle is required to execute this, and also is the impact on the this controller delay. Okay. So, they have plotted this in this graph, right. So, what is that? So, let me just figure it out. So, let us, so if you just put this latency variation. So, as I mentioned this for unroll factor 2, I have get 128. So, initially I have, if there is no unroll, this is 128, right, but if I unroll by 1, then I am getting 96. So, if I just plot this, ideally if you just unroll by 3, this should go down, right. So, it is going down and then finally it is become not exactly this, right. So, I am expecting like this, but your number of time step required is not reducing exactly this way, right. Why? Because this is not linear. So, why this is the case? Because if you just do unroll with, because the actual loop is executing 32 times, if you just do it unroll by 2, now it is going to do exactly 16 times and you can do 2 operations at a time. But if you just do it unroll by 16, again you can do this 16 operations at a time and I can iterate the loop 2 times. But if I just unroll by 17, what will happen? I can do only 17 operations at a time, and the remaining operations 15 I have to do without loop, right. So, another loop I have to do, the trailing loop I have to write. So, that is what is given here. So, if I just do unroll by 16, I have 16 operations and the loop is going to increase by 16. So, this loop will execute 2 times, this is fine. But whenever there is a 17, so I have this 17 operation written here. You can see here this 6 I to 16 and here I to 15. So, there are 17 operations, but if I increase the I equal to I 17 and this I less than 17 will not be true. So, I have to come out. So, from the 17, 18 to from 17 to 31, those operations still remaining, that has to be executed, right. So, that is a trailing loop, what is called and that has to be executed. So, this is cannot be, this has another separate loop and that is actually causing this latency increase, right. So, you can see in this figure 16 has a good around you need around 64 or something, right, 670 kind of, but for 17 I need almost 90 or 95 or something. So, the number of latency does not linearly decrease with the unroll factor, that is clear, right. But what is the controller delay, let us understand now. So, if you just see a genetic data path that is generated, we have a few and there may be marks at the input of FU, and the output of FU go to register, and there may be some marks again, right. So, we have discussed all this structure, and whenever, so what is the controller delay? So, based on the current state, it will generate the next state. So, there will be some delay here, and that signal will come here, it will come here, and it will come here. So, this signal effectively propagate through this multiplexer, this FU to register. So, this is that controller delay path, right. Now, if you increase this unroll, what will happen here? So, as I see the number of state increase, right. So, the complexity of the controller will increase. So, the complexity of delay of this particular thing will increase, right, because now I have a lot of state, the decision making here is bigger. So, the controller delay of the FSM will increase, and also similarly, if you see here, I am doing earlier only 2 operation in chain, now 3 operation in chain, I am now doing 1, 2, 3, 4 operation in chain. So, this chain operation chaining is length is increased. So, that then you have to now put extra marks here and those cases. So, that delay of the data path will also increase, right, because that this multiplexer chain will be now increased, that increasing the sharing of the resource possibility, increasing the size of marks, right, hence the delay. So, if you have just do the unroll, effectively this delay here also will increase, and delay of this path will increase, because the number of marks demarks will come in this path will high, and also the number of operator will come high, right. So, the total delay of this controller will increase, right. So, unrolling is not good for controller delay, right. If you just, so delay will increase, and that is actually plotted here. You can see whenever the unroll factor is increasing, your delay is actually monotonically increasing, which is not like this. So, you can understand that. So, you should have a trade off, right. You cannot just do arbitrary number of unroll, because your computation delay may go beyond your clock period, and in that case you basically the kind of target clock, you may violate the target clock, right, because if your computational delay go very high, say suppose your target clock is 3 millisecond, if it become 4, then when you are actually violating the time. So, your design is not meeting the time step, right. If you just unroll by say 20, you are violating the target clock period, right. So, then this is a serious violation. So, there should be some trade off. So, you can see here probably this is the best choice, right. In this case your latency is minimum, which is 16, but in this 16 also the total delay is say 3.5 or something, and suppose your target clock is 3 point, you are meeting the timing, right. So, this is something the trade off is among this all this this unroll factor, probably I should choose this 16, which is the better choice, or maybe something else. So, based on the target clock, if your target clock is not that high, probably you have to choose this, right, unroll factor of say 8. So, that is the point here, right. So, basically given a design and your target clock period, what this unroll factor you should choose, right. So, that your controller delay is not going so high that it is meeting the time, it does not meet the timing. On the other hand, you have a good benefit in the latency as well. So, that is what is this work all about. This work basically propose an algorithm that will actually find out the trade off between this latency, number of latency required versus the number of computation delay, so that it meets the computer target clock, but you achieve the minimum latency, right. This is what this work is all about. So, similarly, you can look into, if you look into this other work, they are also try to do this kind of advanced kind of checking, just to see, for example, this work actually work on memory hierarchy, right. So, how to improve the memory hierarchy using loop transformation. So, those are the kind of techniques are there. So, this can be used just to utilizing this can be used to utilize your improve your performance of your design, right. So, this is another area of research. So, in summary, we can see that these compiler optimizations are have a significant impact on the generated hardware, and we have specifically discussed 3 kind of work, specifically the data flow based optimizations. We have also discussed some control flow based optimizations, and also we have discussed some recent works on loop transformations and their impact on hardware. And I can say this an active domain of research, and people are trying to find out this impact of this optimization technique in various area, like in memory, in optimizations of the bit width, optimization of the computation time, optimizations of power, optimization of routing length, and various aspects you can always think of having implementing or applying this kind of optimizations, and see their impact on the generated hardware. So, with this I am going to conclude this session, and in the next session we are going to discuss about this RTL optimization technique for power timing. Thank you.